கவுண்ட் எடுக்கிறீங்களா? சொல்லிட்டீங்களா ஸ்டூடெண்ட்ஸ்ட்ட? சார் அப்புறம் எடுத்துக்கலாம்னு சொல்லிட்டீங்களா? மெயில் பண்ணியிருக்கீங்க சார். எனக்கு மார்க்ஸ் சென்ட் பண்ணியிருக்காங்களா அந்த மெயில் பண்ணுங்க சார். அந்த மெயில் அப்புறம் ரீடெஸ்ட் மெயிலும் வந்துருக்கு சார். அதுவும் பண்ணிடுங்க.
Hello, sir. Bibul Kumar, sir.
Yeah, ma'am. You are audible.
Start a session, sir.
Very good morning, ma'am.
Okay. Good morning, sir. Shall we start a session, sir?
Yeah, right, right. We can start it. Like every participant is joined, right?
Okay, they will join, sir.
Okay,
We will.
fine. Then we can
Oh, okay.
start.
Oh, okay.
Okay.
I'm happy to welcome all the participants on the third day of AECT sponsored 2-week FDP on cutting edge trends in deep learning approaches. I'm happy to welcome Bibil Kumar sir, corporate trainer and CTO, Diginiku Tech Labs. He was started his career as a senior research engineer at Times Global Private Limited in New Delhi and now playing the role of corporate trainer. He was delivered more than 40 plus corporate training and faculty development program. His research interest includes embedded networking and electronics, software and information technologies, IoT and cloud, artificial intelligence, blockchain and smart contracts. He delivered guest lectures on various topics such as cloud computing, Python, machine learning, artificial intelligence, IoT, blockchain technologies, etc. He has delivered major training for prime educational venues at IIT Delhi campus, IIT Roorkee, IIT Guwahati, NIT Trichy. He has completed research projects namely electronic meter automation device, energy consumption minimization EV using heuristic learning, video deblurring using generative adversarial neural network, cancer prediction and weather forecasting using data mining, object detection using deep learning and neural network, hand-written image recognition, sentiment analysis using social platforms such as Twitter, TensorFlow image recognition on Raspberry Pi. Today, he is here with us to share his expertise in artificial neural networks. Now, I hand over the session to Bibil Kumar sir. Thank you, sir.
Thanks a lot, ma'am. Very good morning to all of you. So, without losing much time, let's continue with the session because we are having very less amount of time, right? So, okay, let me share my screen first, then I'll continue. Okay, I hope my screen is shared and it is visible for all of you, isn't it?
Visible, sir.
Okay, that's great. So, first of all, let me make a clarity like what agenda that we are having as per the schedule that I'm having. Okay, I have to discuss, just a minute. I have to discuss about artificial neural network. Okay, artificial neural network concept that I have to discuss with you, right? But before getting into the understanding or before getting into the part of artificial neural network, I am expecting that you are already knowing the basics of machine learning, like what are machine learnings, okay, the definitions and all, like how a machine gets learned, what are training set, what are testing sets, right? And how we train a model, okay, what is supervised learning, what is unsupervised learning, okay, what are reinforcement learning. So it is not like that. I'm not expecting that you are knowing everything about it, but I'm hoping that you know that at least definitions, okay, like what is supervised learning, what is unsupervised, and what are reinforcement learning. Apart from that, you might have also worked over with Python, okay, and certain libraries like NumPy and Pandas, okay. So during the previous sessions and all, okay, so I'm expecting that this many things you had worked. I'm not saying that you are on a pro level. I'm saying that you might have just worked a little bit with these particular things, okay? Because if you had worked with little bit with these particular things, okay, and you are knowing the basic concepts of it, then it will be very easy for you. It will be very comfortable for you to carry on with ANN concept, okay? The machine learning is having a thing that is called ANN, okay, artificial neural network, right? We will understand where ANN is required, where we talk about artificial neural network and where it can be used, what are the areas where it can be used, okay, and why it is basically required, right, and how it can be created, okay. That will be a hands-on part, right? So everything we'll discuss in detail. Just let me know a small thing over here, that is there any doubt or anything that you want to discuss from the points that I have already written over here. Just let me know. If anything you want to discuss, you want me to discuss in brief, I will just give a brief insight, because these are important things that need required to be done.
So these topics are already discussed, sir.
Done. Great, great. That's what I want to know. Okay, so let's start with the part. Whenever I will ask you something, do respond because it will make me better. Like I will understand. Okay, things are going well. Okay. So the first thing that we will discuss artificial neural network. Now, question is the very first question over here: why we need artificial neural network? Okay, what are the requirements of artificial neural network? Correct. So look, when we are having certain features, okay, like feature one, feature two, feature three, and then we are having a label. Okay, it can be feature five, feature 10, and number of features can be there. But whatever the features we are having, and we are having a label, what we do, we use this thing as a x, these are y, and we just use this two entity to train our model. Okay, through a machine learning way, like using certain algorithms like classification based algorithm or regression based algorithm. Okay, so it works very better. Okay, but what if the feature size increases to a very extent level? Okay, that means suppose you are having 1000 features. Okay, you are having 1000 features. Okay, then what you can do over here, if you are having 1000 features, in that case what are the things that you can do, how you can treat these things, how you can make a model train? Because obviously then when you are having a huge number of features and you are going with a normal algorithms, okay, that you had already used, the regression based algorithm or the classification based algorithm, it will be difficult for a model to get trained. Okay, it will be difficult for a model to get trained. Why it will be difficult for a model to get trained? Because each feature, like feature 1, feature 2, feature 3, feature 4, okay, feature 1000, okay, like this, each feature basically generates certain coefficients, or you can say certain reference point, or you can say certain weight value. Okay, these features do what? When you train a machine, right, whenever you train a machine, okay, this machine during the course of learning, okay, machine during the course of machine learning, okay, there are certain weights generated. Okay, these features generate certain weights value. Those weights, we can call those weights as a coefficients, we can call those things as a weights, we can call this thing as a reference values. Okay, whatever it is, right? So based upon, because features are going to be constant, okay, labels are also constant. Okay, only if suppose in future any unknown feature is coming, any unknown 1000 feature is coming, then what will be the value? Okay, what will be the output that machine needs to predict? Okay, so how a machine will predict? Obviously machine will predict with the help of the values, the coefficients, the weights, the thing that machine has generated or the algorithm has generated. It will impose these algorithms, sorry, it will impose these coefficients, it will impose these weights, it will impose this reference value over the features it received. Okay, it will impose these things over the feature it will receive, and based upon certain equation that is used during the course of learning, okay, based upon certain mathematical equation that is used during the course of learning, okay, the predictions will be made. Okay, but the challenge over here is, we are having this many features. Okay, so if we are having 1000 features, we will have 1000 coefficients. Okay, or say in somehow you can increase it to 2000 or something like that. So 1000 coefficients or 1000 weights, okay, to represent a machine. Okay, if we are having 1000 features and we are using any machine learning algorithm, okay, then we will have 1000 coefficients or 1000 weights. Okay, it can be deferred, it can be, I'm not saying 1000, it can be 900, it can be 1200, it can be 2000, depends upon algorithm to algorithm. It totally depends upon algorithm. There is no fixed number that you can say, okay, 1000 will only be there, but ultimately I have to give a number, that's why I'm just giving a number 1000. Okay, but anyway, it will be in a range of 5500 to 2000 or 52500, like that. Okay, so whatever the number it is, whatever the number it will be in a range of suppose 500 to 2500. Still these many weights or these many coefficients are not enough to represent all of these features, or all of the, you can say, all of the conditions, all the conditions or all the possible conditions. Okay, these many weights are not enough to represent all the possible conditions, right? That's why the need of artificial neural network came. Okay, people thought that we can create artificial neural network where we can increase the model size. Okay, what people thought, like suppose we are having there are two cases. Okay, what are those two cases? Let me tell you. Okay, there are two cases. Case one, where this is your feature size, and this is your model. Okay, so over here the feature size is quite big, model size is quite small, right? Model size is not fitting into the situation. Case two, this is your feature size, okay, and this is your model. So this case is known as underfit model. Underfit model, that means you are having huge number of features, you are having huge number of samples. Features and samples are two different things. I hope you understood, right? You are having a huge number of features, you are having a huge number of samples, but your model is not enough. Okay, your model, your size of your model is very small. Size of your model means what? Means the weights that is required by your model. Okay, the weights that are required by your model, the coefficients, the values that are required by your model, okay, that is basically generated with the help of certain calculations. Okay, those number of weights, those number of values, those number of coefficients are very less in number. Okay, so that's why it is an underfit model, because your model is not defining everything of your sample. Okay, it is not defining everything of your sample. Now it is known as overfit model. Overfit model means what? It is your feature size, or you can say, okay, it is your model size. That means what? Over here your model is quite, it is much bigger in size as compared to your samples and feature size. Okay, your model is much bigger in size as compared to your sample and feature size. Now question is, why it is much bigger? It is very the model size increases because the number of coefficients, number of, you can say, the weights, the number of values that is representing a model is huge in number as compared to your, excuse me, as compared to your features given. Okay, suppose you had given 10 features and you had generated 100 different coefficients that is representing a model. Okay, you are having 10 features and you have generated 100 coefficients that is representing a model. Obviously your model has increased, the size of your model is very big. That means for every like kind of feature there are 10 weights values. Okay, so in that case what happen, it will be like, this will give you, you can say, a highly accurate model. Okay, but the highly accurate model will be limited to the case of given data only. Okay, if any unknown value will come, okay, any unknown value will come, when this model will be deployed for the real time use, this model will just get failed. Okay, this model will just get failed because it is suitable for the limited set of data. Okay, that's why we need a optimum situation. Okay, or we need a balanced situation. Okay, we need a balanced situation where your data can fit. Okay, your data can satisfy the model size. Okay, your data can satisfy the model size and your model size can satisfy the data, right? So that's why the case neural network was used. That's why the case the neural network came into the existence. The first thought was given like that, why not to create a machine learning model that can work like a human neuron system, that can work like a human brain system. Okay, so human brain system is what? We are having a brain system, we are having a neuron system where neurons are arranged. Okay, neurons are connected through veins. Okay, that means we are having a sense organ senses those information are basically captured by neurons. Okay, sense organs are connected with the neurons, so those informations are captured by neurons, and then it travels through veins. Okay, and it travels through veins and reaches our brain, and in the brain it processes, and then we understand, okay, what's going on around us. Okay, then we detect this physical world, right? So the same thing happened over here. Okay, that means it was thought, why not to create a situation that can work like a human brain. Okay, and then the concept of neural network came. Okay, neural network came. Okay, so the first model that was proposed was known as perceptron model. Okay, perceptron model. Okay, so I will show you perceptron model better. Okay, just a minute. If you want to see perceptron model, there are n number of, you can just go over here. Okay, and if you just type in Google, you will get the image of perceptron model. Okay, I will also show you. This was used earlier, nowadays no one is using it, but still we should know it because it's a history from where things started. Okay, So you can see a perceptor, and these are all images of percepted model. Any image you can consider, all are same thing. Okay, you can see over here. Suppose this one, simple one. Okay. Okay. So what it is saying actually to us? Let me tell you. Over here, you can see there are two entities: x1, x2, x3, x4, x5. What is x1, x2, x3, x4, x5? These are known as your features. Okay, when you train your model, you need a features. Okay, so these are known as your features. Okay, and these are known as what? These are known as your weights. Okay, weights. That means when these features will combine with the weights, output will be calculated. Features will be given by you. Okay, features will be given by you because you are having a data set. In that data set, features and labels you are having, right? And weights will be, and from where weights will come? Weights will be earned. Okay, weights will be earned by model using algorithms. Okay, weights will be earned by the model using algorithm. What algorithm? That I will discuss. Okay, that means weights will be calculated, and this weight actually represent your neural network. Okay, these weights actually represent your neural network. That means when you train your model will use the algorithm, generate the weights or define the weights, and will save these weights. Okay, to give a best possible accuracy. Okay, and when the weights will be saved, so these weights will be used with the future, with the further features to make the prediction. These weights will be used by whom? These weights will be used in the future to make the predictions, to give someone an output, right? Okay. Okay, so it is the basic concept. Okay, so let me elaborate it more. Okay, suppose just consider a simple case. Okay, where you are having a kind of a situation. Okay, there is a person who is, I'm having a data set. Okay, that data set is representing certain things, like someone is there are certain alumni of the college or some like past data. Okay, representing like data of 100 students. Okay, like how many assignment he did, how many attendance, what is the attendance. Okay, and the remarks in the class, the remark in class. Okay, and it is a final result. Okay, final result, like his pass or fail. Okay, so assignment, suppose out of 100, out of 15 assignments, someone did 12 assignments. Out of 30 attendances, someone is having 25 attendance. Remarks suppose like the 3 marks, 1, 2 and 3. Okay, 3 is the 1 is best one, 2 is the next one, and 3 is the worst one. Okay, so he is getting remark and he passed the exam. Okay, so over here the pass is what? It's output, and these 3 will act as a neurons. Okay, that means these 3 will arrange like this: 12, 25 and 2. Okay, and these will be connected with the output, since it is a what? It is a supervised learning process. Okay, so it is a output. Okay, in the output, what will be like? Pass is represented by suppose 1. Okay, and fail is represented by 0. So at the output the value is 1. Okay, then what will happen? Here weights will be defined. Okay, weights, weight 1, weight 2, weight 3. Okay, so here weights will be defined. How weights will be defined? Suppose here the weights is 1, here weights is 2, and here weights is 3. Okay, that means the final output will be what? 12. Okay, 12 multiplied by 1 plus 25 into 2, 50, plus 2 into 3, 6. Okay, it will be what? It will be your 68. Okay, so here the output is what? 68. Correct, here the output is what? 68. Thereafter, at this point, okay, at this point actually 1 is required. Okay, that means your model will do what? Your model do the calculations with some random weights values. Okay, and then some value is calculated. Thereafter, this will be compared with the actual output to figure out the error. That is what happened in supervised learning, isn't it? First model get trained, okay, calculates the output, then that output compared with the actual label, errors figured out, and thereafter errors get optimized. That is the whole process, isn't it? So over here also 68 will be compared, but how 68 can be compared with 1? 68 is a very huge value. So over here something is used that is known as activation function. Okay, here we use activation function to figure out the things. Okay, so what activation function we can use? We can use like kind of a logistic regression function. Okay, that is also known as sigmoid function. Okay, sigmoid activation function, right? So when we use sigmoid activation function, what we will get? We will get a value in the range of 0 to 1. Okay, if we use sigmoid activation function, we will get a range between 0 to 1, and based upon the threshold value, it can be decided that 68 is representing 0, 68 is representing 1. Okay, so if you had gone through sigmoid activation function, well and good. If not, okay, then in future you may see this thing, sigmoid activation function. Okay, whenever sigmoid activation function applied on any number, it gives a value in the range of 0 to 1. Okay, it gives a value in the range of 0 to 1, like this: 1 upon 1 plus e to the power minus x. Okay, so here x will be represented by 68. If x will be replaced by 68, okay, obviously you will get a value of between 0 to 1, right? Now if you are having a value from 0 to 1, okay, like this, right? So suppose you are having 500 samples. Okay, so for these 500 samples, right, like for this whatever, all of the sigmoid values are sigmoid function will be applied and certain value will be calculated. Okay, suppose all those values here, suppose you are getting 0.6. Okay, for some case you are getting 0.5, 0.3, okay, 0.2. Suppose for the all values above 0.6, okay, all the values above 0.6, okay, is representing pass. Okay, and all the values below 0.6 is representing 0. Okay, so in that case your machine come to know that 0.6 is the threshold value. Okay, and 0.6 can be used for making a prediction, as well as machine understood that what weights can be given. Okay, these weights will be optimized to give you a minimum possible error, right? So it was the first perceptron model that was given. This whole thing is known as perceptron. Okay, this whole thing is known as what? Perceptron, right? But later on it was thought like perceptron model is like whatever perceptron model we are discussing, it is almost similar to your machine learning model. There is no such a big change over here. Okay, it is almost similar to your machine learning model, isn't it? It is working almost similar way. Okay, here also you're calculating the weights and a kind of a simple algorithmic model, like any, if you talk about KNN, SVM, decision tree classifier. Okay, so there also we used to calculate some weights values or some kind of a references values. Okay, based upon that model predicts. So here also for 5 features there are 5 weights. Okay, so things are limited over here. Okay, for 5 features we are having 5 weights, so it's good. For 5 features 5 weights are enough, but for 100 features 100 weights are not enough. In case if you are having 100 or 1000 samples, okay, in that case it is not enough, right? So that's why it was thought like, okay, initially we were not having that much powerful computer systems, we were not having that much powerful storage spaces, we like cloud things were not there, big data things were not there, so much advanced computer systems were not there. That's why perceptron model was thought. But later on, when the when the more powerful system has been created, more powerful processors has been created, okay, and later on people creates a kind of a more the processing power of the systems increases. Okay, then we thought of something that is known as neural network in better way. Okay, thereafter from perceptron model neural network came out. Okay, so let me discuss now the actual neural network. Okay, so it was the first story of a perceptron model. Okay, you can see over here n number of example, you can see over here, you can see the input, weights, weighted sum, and then a step function. Okay, so here they have used a step function. Okay, you can use a step function, you can use a that one also, sigmoid function. Okay, so it's just your choice that what you want to use. Here, look here, in this image sigmoid function is used. Okay, in this case sigmoid is used, in some cases step is used. Okay, but for the maximum cases you will see sigmoid only. Okay, it depends. Okay, so this is how things works. Okay, in case of perceptron model, right? So what we discovered, we learned from this particular concept, that in case of initial neural network, or the first, or you can say the first proposed neural network, okay, features were used to calculate, to make a machine learn. And what the machine basically learns, machine learns the weights. Okay, machine learns about weights, and those weights are basically representing your those weights basically represents your complete model. Okay, then it comes neural network. So in neural network there are so many concepts came. Okay, the neural network basically created not with just kind of a perceptron model or something like that. There are so many things that we need to know in neural network. Okay, the actual neural network that we are currently using. Okay, so let me tell you what are those ways. Just a minute. Okay, so there are certain terms we should know, like neurons, input neurons and output neurons. Okay, then second we should know about hidden layer. That is very important. Without hidden layer there is no neural network. Okay, third we should know about feed forward network. Feed forward network. Okay, fourth we should know about backward propagation. Okay, so we are having neurons, hidden layer, feed forward network, backward propagation, then sorry, activation function. Okay, sixth, optimizations. Okay, so these are the basic concepts, these are the basic terms that there are so many n number. It is not just 6 or 7 terms. Okay, let me tell you, it is not just 6 or 7 terms. It is n number of, there are n number of concepts that came into neural networks that we should know. Okay, like regularizations are there, normalizations are there, right? So there are n number of things there are there. But all of a sudden I will not bombard everything all together. But these are the most important thing that we should know at the first step. Okay, so first of all, what are input layers? Okay, so let me tell you the features. Okay, the number of features will act as your input layer. Okay, so if you are having n number of features, those features will be represented by the neurons. Okay, feature 2, feature 3, feature 4, feature 5, right? And then we are having an output layer. The number of outputs, okay, the number of possible outputs will be represented by your output layer. Okay, these are your output number of possibilities, correct? Now we will connect them. So when we connect them, it will be again similar to the previous one. Okay, like previously when we define the things, okay, it is almost working, it is also representing, or you can say behaving like the previous one. Then what is the difference between the previous one and this one? Okay, so let's see. We will define over here something that is known as hidden layer. Okay, it will come over here as a hidden layer. Okay, so this hidden layer basically helps in increasing the number of weights that a machine can learn. Okay, these hidden layers helps in increasing the number of weights that a machine can learn. That is very important. Okay, that means what? If the weights which were directly connected to output layer, now those weights are not directly connected to output layer. These weights are getting into, these weights are getting connected with hidden layer first. So if you consider the previous case where your neurons were directly connected with the help of weights to the output layer, okay, so that was case 1. So in the case 1, the situation was like this. How many weights was possible? There are 5 neurons and there are 2 outputs of 5 cross 2 plus 2 bias, that can be 12. Okay, in first case only 12 weights were possible. Okay, in this case you can see how many weights are possible. Okay, you can easily calculate now. Okay, so you can see over here 5. There are 5 things or 5 features. It is connected to a hidden layer with 3 neurons. Okay, that means there can be how many? That was known as biases. 3 biases will also be there. So 5 cross 3, 15 plus 3, 18. Okay, that means on the first layer only it is 18 number of weights that a machine can learn. Okay, here machine can learn how many weights? Here machine can learn 18 number of weights. Machine can learn how many weights? Here machine can learn 18 number of weights. Now go to the next case. In the next case, it is 3 cross 2, isn't it? 3 cross 2, 6. 6 plus 2, 8. 2 is what? Bias. Okay, 3 cross 2 plus 2 is equal to 8. Okay, that means 18 plus 8 is equal to 24. So case 2. So you can see, if you are using normal perceptron model or any kind of a normal ML model, you are having just 12 weights. That means to reach a destination you are having 12 paths. 12 weights means what? You are traveling somewhere, and to reach a destination you are just having 12 paths. Through 12 paths you can reach your destination. Okay, you can choose any of those paths. Okay, you can combine those paths all together. Okay, you can use in this neural network, these are weights or what? These are certain values. Okay, these values will be manipulated, will be changed. Okay, will be learned during the course of learning, right? So there are only 12 values that a machine can learn. So if a machine can learn only 12 values, then obviously machine will have little bit more error and little bit less accuracy. But in second case, when we applied neural network, now machine is having 24 different values that a machine can learn to represent a model. Okay, here a machine can learn 24 different values to represent a model that can predict certain thing. So things get just doubled, right? So obviously if 24 values that a machine can learn, it will increase its accuracy, it will decrease the error that is possible, right? That's why a neural network was thought of. Okay, to increase the possible number of weights, to increase the possible number of accuracy that a machine can, explore, right? So what we had seen, this is your input neuron. Okay, these are your hidden neurons, and these are your what? Output neurons. So three things are done, correct? Then we are having feed forward network. What are feed forward network exactly? Okay, so let me tell you about feed forward network. It's very simple. Let me draw a simple way. Okay, 3, it is your output, right? So it is connected with this one, correct? And so it is what? Hidden layer 1, and it is what? Hidden layer 2. These are your input layer 1, input neuron 2, input neuron 3. Okay, so these are connected like this. Okay, so hidden layer 1 is equal to what? Input layer 1 into weight 1 plus input layer 2, sorry, input neuron 2 with weight 2 plus input layer 3 with weight 3. Okay, hidden layer 2 is equal to what? Plus some bias. Okay, B. Hidden layer 2 is equal to what? Input layer 1 into weight 4 plus input layer 2 into weight 5 plus input layer 3 into weight 6 plus bias. Okay, so finally this is what we are having, right? And these are weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, correct? That is defining the weight of these particular neurons, like which neuron is highly important and which neurons are less important. Weight means what? The value, the importance of a particular situation, correct? So these weights will define for a particular condition which neuron is quite important and which is less important, right? So it is what? It's a feed forward network. Feed forward means what? First hidden layer is calculated, and with the help of hidden layers the output layer will be output neuron will be calculated. Okay, so output is equal to what? H1 into weight 7 and weight 8. Okay, H1 into weight 7 plus H2 into weight 8 plus bias 3. Okay, so what is it? First this one is calculated, okay, and next this one is calculated. Okay, so that means we are moving in a forward direction. Okay, so that's why it is known as what? Feed forward process or feed forward network. That means at each layer, okay, each layer is feeding the next upcoming layer. Each layer is feeding what? Each layer is feeding the next upcoming layer. Okay, that is a feed forward network, simple, or feed forward process, correct? Next we are having backward propagation. Okay, next topic is what? Backward propagation. What is backward propagation? Backward propagation means what? Optimizing the error. That means at the output, when output is calculated, there will be a error can be calculated. Error means what? Here output calculated, this output will be compared with the actual output. Okay, that means actual label, I should say. Okay, because it's a supervised learning, right? So this will be compared with what? Actual label. Okay, and when it will be compared with actual label, the error, the difference between it is known as error. Okay, and to minimize the error, the backward propagation will goes on. Okay, backward propagation will goes on by using gradient descent or any other optimization technique. Okay, so let's see how a backward propagation goes on. Okay, that means what? Suppose output value calculated is 100. Okay, this is your output. Okay, actual label suppose is what? 80. Okay, so error is what? 100 minus 80, right? It is your error. This will be equal to 20. So these errors are depending upon what? These errors are depending upon only one factor that are known as weights, because these errors are not depending upon the features value, because features values are constant, right? You can't do anything with the feature. Correct. If the temperature is 55 degrees Celsius, then it will be obviously 55 degrees Celsius, right? To decrease the error, you can't make it 54 degrees Celsius, right? Because features will always be the same. Okay. The only thing that you can tune, okay, is weights. Okay, you can just tune the weights to increase or decrease the error, right? So that means this error is depending upon what? Weights. So what we do? We partially differentiate error with respect to weight. Okay, like we should partially differentiate error with respect to it. Now question is why? Why we will differentiate error with respect to it? It is because, just consider a case, okay, over here, where your y-axis is representing the error that you are getting, x-axis is representing weights that basically you are changing or you are tuning. Okay, you are continuously tuning the weights value. Okay, and y-axis is representing the error value. In this case, if you will suppose errors are continuously changing, okay, and weights are also changing, increasing, decreasing, or somewhat you are doing. Okay, so weight changes and weights, and as you changing the weights, this is how things are changing. It is not going to be such ideal. Obviously it will be something different, it will increase, decrease and all, so many things will go on, but still I am considering the ideal case at first so that we can understand it in a better way. Okay, so this is the ideal case. Okay, just consider the ideal case. Correct. Just give me 1 minute of time. Okay, so this is the ideal case. So this ideal case is telling us what? It is telling us that it is your minimum possible error value. Okay, it is telling what? It is telling us it is your minimum possible error value, right? That means if the weight will be present over here, if whatever weights that are present over here, if I will use that particular weight, we will be at a minimum possible error. So anyhow we have to reach over here. Now question is, how can we reach over here? Who will help us in reaching over there? This particular thing will help us in reaching over there. How? Let's see. If you are having certain weights, there are so many weights. How many weights were there? There were 24 weights, or in the previous example it was 3 3 6 plus 2 8 plus 2 10 1 11. 11 weights were there. Okay, so those 11 weights you were tuning, right? Suppose for a particular weight, this is a graph. Okay, this will be done for each weight, and this will be done for each of the weights that are present, and optimum or balance situation will be generated. How? I will explain. So it is your curve. We are considering this thing as a curve between error and weights. Okay, now on a particular curve, right, on a particular curve, if there is any curve, okay, and on that particular curve, if you have to calculate the slope of a tangent at a particular point. Okay, slope of a tangent at a particular point means what? This means, suppose at this point I want to draw a tangent. Just a minute. I want to draw a tangent. So I drawn a tangent over here. Okay. Now, if I had drawn a tangent over here and I want to calculate the slope of this tangent, so what can be the slope of this tangent? According to coordinate geometry, it's very simple. The slope will be what? Okay, it's very simple, right? Slope of the tangent will be dE. That means partial derivative of error with respect to weight. If y-axis is representing error and w-axis is representing, sorry, x-axis is representing weight, okay, or dy upon dx, or dow y upon dow x, okay, whatever you can tell it, right? So basically this is a tangent, right? So what we do, we write a equation, weight is equal to, or you can say weight new is equal to weight old minus just a minute. Better? Weight new is equal to what? Weight old minus dow E upon dow W. Okay. That means what? Whatever the slope that you are getting over here, this slope is governing your machine to learn the weights. Okay. During the course of backward propagation. That means feed forward networks run. Okay. When feed forward networks runs, this is what you calculated. This is output. This is your actual label. Okay, and this is your 80. Okay, the difference between it, this thing was 20. Okay, the same way for different labels, there will be different weights. Okay, there will be different errors. For different weights, there will be different errors, right? Now we need to find out a point where we can get a minimum possible error. So we start calculating this particular value. This value will represent a tangent, a slope of a tangent on a graph. If on a slope of a tangent on a curve, okay, in between errors and weights, okay, and this will be represented, and this particular thing, this gradient, okay, it is also known as gradient, okay, this is known as gradient, right? So this gradient will be used to control the learning. That means with the help of these gradients, your weights are changing, okay, your weights are continuously changing, okay, and this is known as what? Backward propagation. So during the course of backward propagation, your weights will keep changing with the help of this particular formula. Okay, so that means first weight was over here, second weight will be somewhere over here, right? Somewhere over here, according to the value of this tangent, according to the value of this particular thing. The next weight will be someone over here. Why? Because you can see this tangent will have a at least negative. If you see the tangent, you can easily say that this will obviously will have a negative value. So if it is having a negative value, then negative will be what? Okay, it will be added on. That means first weight was over here, then obviously the next weight will come over here. Okay, then over here, then over here. Then when you reach at the minimum possible weight, sorry, minimum possible error, when you reach at the minimum possible error, after this error starts increasing again. Okay, so at minimum possible error, what will happen? You will get a horizontal line, and if you are getting a horizontal line, you know the slope of horizontal line is almost equal to 0. Okay, if it is almost equal to 0, that means this value is almost equal to 0. Okay, if it is almost equal to 0, that means weights will stop changing. Okay, that means if you try to move on this side, automatically this formula will again pull back you. Okay, it is like a curve, it is like a hill, okay, where you just throw a ball. Okay, that ball we can rotate anywhere, but ultimately ball will stop over here. Okay, same thing, if you started from here, you stop over here. If you start from here, then also will stop over here. Okay, because ultimately because of this formula, it will come in downward direction. Okay, because over here the slope will be what? Negative. If the slope is negative, sorry, over here the slope is positive. Okay, in this direction the slope is positive, the value of this thing will be positive. If this is positive, that means this value will be positive, that means it will continuously decrease the weights. Okay, so if you starts from here, you are moving in this direction. If you starts from here, you are moving in this direction, right? So ultimately you stop over here. Okay, a point, your model will get trained in such a way with the help of optimization process, with the help of gradient descent, that it will optimize itself and will reach a minimum error point. Okay, and at minimum error point, you can say weight new is almost equal to weight old. Okay, that means there will be not so much changes in the weights. Okay, and then we say that okay, my machine get learned, and we just stops our machine learning, right? Or automatically it will stop, because obviously if value is not changing, then automatically the learning stops. Okay, the learning continue only till the point where the values, where the weights are changing. If weights are not changing, that means learning stops, learnings are done, isn't it? So it is how it performs, right? So what we have seen till now, we have seen certain points. Okay, first, input neurons. Okay, just a minute. Input neurons, output neurons. Okay, hidden layer. Okay, weights, that represents a neural network actually. Fourth, feed forward network, or feed forward process. Okay. Fifth, backward propagation. Okay, and sixth that we have to see is known as activation function. This is very important, right? So after all these things, activation function is one of the very important fact that we have to understood. Okay, what is activation function actually, right? Just a minute. Okay, so let me tell you about activation function. What is it? Activation function basically applied over the neurons. It can be hidden neurons or the output neurons. Okay, but why it should be applied? Okay, the question is why it is getting applied. Why? What is the requirement of activation function? Okay, so basically activation functions in general term, if I have to define it, what activation function do? Activation function in just two words or in three words is, it can be defined as, it breaks the linearity. That's it. It just breaks the linearity. Okay, wherever you are getting a linear output, okay, or you are on a linear playground and you want to break the linearity, it is activation function who will breaks the linearity. Okay, no one else. Okay, activation function is going to breaks the linearity. That means what? Just see. Okay, that means what? Suppose you are having these input neurons. Okay, and these are your hidden neurons. Okay, and these are your output neurons, right? Now what you did, you calculate the values over here. Okay, with the help of weights, values are getting calculated, the hidden layer values are getting calculated, right? The hidden layer values are getting calculated. Weights 1, sorry, h1, h2 and h3. Okay, you have calculated h1, h2 and h3. Okay, now the challenge over here is these weights are regulating h1, h2, h3, correct? Now these weights are basically used like this: input into weight 1 plus input into weight 2, input 2 into weight 2 plus input 3 into weight 3 plus input 4 into weight 4, okay, plus bias. Okay, so certain values are coming. Okay, so it is what? It is like a linear equation, isn't it? If it is like a linear equation, then obviously the values are not, you can't control it. The values can be from negative to infinity to positive infinity. That means these hidden layers values can be from negative, negative possible infinity to positive possible infinity. Like it can be anything. These hidden layers values can be anything, right? From negative infinity to positive infinity. Okay, that means during the course of feed forward process, output calculated, and during the course of backward propagation, these weights are getting tuned. Okay, they are changing itself to get the minimum possible error. Okay, and during the weights are changing itself, the hidden layers can gain the value. Those value can have a range from negative infinity to positive infinity, anything, right? But the challenge over here, if we keep using this particular way, it may possible that your process is running quite wisely. Okay, it is the back propagation is also going on and weights are also changing, but it may possible that if like suppose it is 10, it is minus 5, it is minus 3. Okay, and in the second round what happened, this becomes 10. Okay, this becomes minus 5 and this becomes minus 3. Okay, that means the neurons are changing its the value of neuron is also changing. It means what? Feed forward network goes as it is, the backward propagation is going well. Okay, everything is going well, but ultimately the values of neurons is not changing properly. Okay, because the cumulative output remains same. Okay, what I want to say, the cumulative output remains same. Okay, individual neurons are changing its value. Okay, individual neurons are obviously changing its value, but the cumulative output remains same, or the cumulative output is not changed a lot, it is changing in very small proportion. Okay, so that means it is like a condition where your processes, your system is doing a very hard work, but ultimate output is not changing. Okay, at a certain point of time things gets constant or things gets stable. Okay, that means uh, it is just all the task, all the processing is just going in, it just went into the waste. Okay, so what we need to do, we need to apply a activation function over here. Okay, we need to apply a activation function over here to deal with the situation. Okay, so what is that activation function? Activation function over here that we apply is known as ReLU activation function. ReLU means what? Rectified linear unit. Okay, rectified linear unit, right? That means what it will do, it works like this: f of x is equal to 0 if x is smaller than 0, smaller than or equal to 0. Okay, and f of x is equal to x if x is greater than 0. That means what? Over here, if the values of neurons are positive, it will remain as it is. But if the value of neuron at any point of time is calculated negative, that will be converted into 0. Okay, that means all negative neurons, your system, your model will consider as a 0. Okay, all negative neurons will be considered what? All negative neurons will be considered as 0. This is how your rectified linear units works. That means ultimately what you did, you break the linearity, isn't it? You just broke the linearity over here. Okay, so that means what? Activation function is created or is used just to break the linearity at every layer. Okay, so just like only one activation function are there? No, there are n number of activation functions are present. Around 8 or 9 activation functions generally we use. Okay, according to different requirements. Okay, and all of those activation functions are having different formulas actually. Okay, for example, at hidden layer I told you ReLU can be used. What ReLU will do, if at a hidden layer any neuron get negative value, okay, it will break the linear structure of the complete neural system. It will break the linearity and negative value will be converted into what? 0. Correct? Then at the output layer, come to the output layer. Okay, so at output layer, suppose it is your output neuron. Okay, it can be like a number of hidden layers are there, right? They are just coming over here, right? It can be like this. Okay, so these are output neurons. Correct? So what kind of activation function used over here? Okay, there is activation function called sigmoid, that is using logistic regression. Okay, so I told you the equation of sigmoid. What sigmoid will do, whatever the value that will come out, it will convert that thing into 0 and it will convert the value between 0 and 1. Okay, it will convert the value between what? 0 and 1, and based upon the value of 0 and 1 it can be decided that yes or no. Okay, based upon the value, suppose 0 and 1 is calculated, suppose the output calculated is 0.5. okay, so if it is more than threshold, then that will be considered 1. If it is less than threshold, that will be considered 0. Right, the same way there is one more activation, two activation function we had seen, ReLU and sigmoid. There is one more activation function called softmax. Okay, that is used at the output layer, and so many times it is very successful also actually. Okay, it is very successful also. Okay, how? Let's see. Suppose at the output layer we are having 3 neurons. Okay, that means 3 possible conditions are there. Correct? So these 3 neurons are there. That means the model will get trained and it will predict out of 3 conditions, any one condition will be predicted by the model, right? So the suppose condition is A, B and C. Suppose the first sample is representing A. Okay, first sample is representing what? A, isn't it? So if first sample is representing A and A is represented by 1 0 0, okay, B is represented by 0 1 0, that means here the values we are representing in binary terms. C is represented by 0 0 1. Okay, so just imagine the first sample is representing A. Okay, that means when the first sample, the feature of first sample is feed over here. Okay, when the feature of first sample is feed into this particular neural system, okay, feature of first sample is feed into neural system, that is representing A, that means it is the first sample is representing 1 0 0. Okay, now the output of neurons calculated, suppose the output over here calculated is 10 15 minus 5. Okay, then how it can compare with the actual level? Actual level is 1 0 0, but the calculated output is 10 15 and minus 5. Okay, what we can do for it? Okay, what we can do? Okay, or suppose it's minus 15. Okay, or suppose it's minus 25. Okay, I'm just giving it a value, suppose minus 25. Okay, so what we can do, there is one idea that we can calculate the probable existence of each neuron, probability of first neuron, probability of second neuron and probability of third neuron. Okay, and then we can arrange them and then in the vector, and then you can calculate. That means suppose the probability of first neuron, second neuron, third neuron we calculated, and over here it is coming suppose 0.3 0.5 0.2 like this. Okay, I'm just supposing, please don't take it like it is actual value. So over here we figured out that actual value is 1. Okay, so the probability of this thing should be higher, so model will make sure, model will again go, back propagate. Okay, model will again back propagate to make this probable value higher as compared to others one. Okay, during the course of feed forward process, this is what calculated, then model will back propagate so that the probable value of this neuron can be higher by changing the weights. The probable value of the first neuron can be higher because actual level is representing 1 at the first position. Okay, this is the possibility, but over here we can't use it directly like this because of negative neuron. Okay, because the third neuron is having a negative value, correct? And we are using a linear equation, so since we had break the linearity on the hidden layer. Okay, we breaks the linearity at the hidden layer, but again after hidden layer the weights are also present, so these weights are again combined in a linear way. So that's why you are again getting there can be possibility that we can get a negative as well as positive value. Okay, we can get anything over here. Okay, so that means calculating a probability over here is not that easy. That means we can't calculate a probability like this. Okay, we can't calculate like this, isn't it? As well as we can't make this minus 25 into positive 25. We can't make it, right? If we make this negative 25 into positive 25, then what will happen? The complete meaning of these weights we are just changing. Okay, the complete meaning of weights we just changed. Okay, these weights are representing that this neuron is having a highest value, and this neuron is having a second highest value, and this neuron is having the lowest value. Now if we just change the sign, then what we are doing, we just ignoring the importance of these weights, and all of a sudden this neuron will have a highest value. So that is just reversing the situation. That also we can't do. We can't convert negative value into positive value directly. Okay, so here certain kind of activation function used like this, e of 10 upon e of 10 plus e of 15 plus, so exponential values, or you can say the logarithmic terms we use. Okay, we use logarithmic terms or exponential value to calculate the probability, so that negative value can also be considered. Okay, and ultimate output will be between 0 to 1. Okay, and that will give you the probable value. Okay, here e to the e10 e15 plus e negative 25. This is known as softmax. E negative 25, E10, E15, E negative 25. Okay, and thereafter, if these are the value calculated, okay, in that case, you can say that what is the error? The error over here is 1 minus 0.3. Okay, because 0 minus 0.5 it is negative, model will ignore. 0 minus 0.2 negative 0.2, model will ignore. 1 minus 0.3 0.7 positive 0.7, model will accept. Model will say, okay, I am having an error of 0.7. Okay, that means I have to go back, okay, and I have to again tune the value of weights so that this error can be decreased. Obviously, when this error will be decreased, okay, there is only one way through which you can decrease the error. Okay, there is only one way through which you can decrease the error. What is that way? You have to increase this value. Okay, you have to increase this value. So model will do what? Your algorithm will do what? It will continuously feed forward and back propagate, feed forward and back propagate, feed forward and back propagate, to continuously increase the probable value of this thing, okay, to a maximum possible extent. Why? Because label is saying 100. Label is saying that for the sample it is a means what? 100. That means it is 1, it is 0, it is 0, right? So that is how your error can be calculated, right? So what we understood? We understood that activation functions are used, okay, activation functions are used over kind of neurons, okay, in your neural network model, over neurons in your neural network model, to break the linearity and make your model and make the predictions through your model during the course of learning, right? So this is what the first basic concept that we should know. Apart from this, there are a lot many things are there that we will understand. All the things we should not like start from the very beginning. It is not like that without creating any kind of things, and we should know every theoretical concept at the starting. First of all, we should, because these many things are very important. If we are knowing these many things, then we can continue, okay, then step by step we learn further things. Okay, step by step we learn further things. Now out of this, if you're having any query, please do ask so that I can proceed for the next part. Let me take your query. You can put in the chat or you can speak out also. Okay, okay, I hope it is clear, so we can continue, right? What we can do, we can take a small break now, because I will now tell you how we can create a program for that. Okay, because so many things we have to understand. So before going with a further theoretical concepts, okay, I want that whatever we understood, we can deploy it. Okay, you can create a program for that, and then we proceed for the next part, right? So before continuing with the program, I will just take a small break, and thereafter we'll continue. Will it be fine?
Okay, sir. We will have
Okay.
a break.
Okay, so 10 minutes break is fine.
Okay, sir. 10 minutes break.
Okay, so it's 11:15. By 11:15 or 16 we'll resume back. Okay.
Okay.
Okay. So, hi everyone. Am I audible?
Yeah, it's audible. It's audible.
Sir, I have a question.
Yeah, please, please.
Uh, when we apply transfer learning, actually we are not training the intended image. Some because we have low number of samples, we used to give some other images and we will be training.
Obviously, right.
How far it will be fruitful?
The fruit,
Uh,
fruitful. I'm not getting a question. Like fruitful for what? Fruitful for model.
well, different kind of images have different kind of features.
Mm-hmm.
Uh, Training a different kind of image and then applying some other kind of image, will it be helpful us to find extract useful information from the image?
Got your question. Okay. I will explain now. Okay. So when we use transfer learning kind of things, right? Suppose we had used a sample set of images that is going to be, that is going to, why we use transfer learning? First of all, we use transfer learning for making your model more concrete. Okay, to make your model more concrete. Right? For example, you suppose you trained a model for handwriting recognition. Okay, so for handwriting recognition, there will be a kind of it will be like this. Hello, how are you? Okay, suppose this is what
Yes,
on this.
sir, I'm listening. Yeah, I'm
Yeah,
listening.
yeah. So suppose like this kind of, we use this kind of different handwriting patterns. Okay, suppose we use 1000 handwriting patterns. Okay, and for all these handwriting patterns, right, what we did, we are using English language. Okay, for all these handwriting patterns we are using English language, and we make a model. Okay, and thereafter we are training it. Okay, and once we trained, right, what happens, your model is created to recognize your handwriting. Okay, like in future if someone is writing, then his handwriting can be recognized, but it is having a limitation that it can only recognize the English handwriting, right? That means if you create a model and this learning you want to use, for the further, suppose further you got more samples, further you suppose like in future also, like people are writing, and then you want to use those images again. Okay, suppose in future this model is deployed, and after deployment is working, and during the course of working, or during the course of its actual functioning, okay, people are again writing something, so their handwriting, it is not necessary that their handwriting will be exactly same to the handwriting that we used in the model. Okay, their handwriting are not, it is not important, it is not mandatory that those handwritings are going to be exactly same that is used in the model. Okay, so there can be some different things that are coming in into the ground. Okay, so but your model is using the learning that it basically got during the, like from model 1. Okay, like model 1 is having some kind of weights. Okay, and with the help of the knowledge that it gained from model 1, it is using that particular knowledge to make a predictions. Okay, so that predictions can be correct, or that prediction can be incorrect. Okay, that prediction can be correct, or that prediction can be incorrect. Okay, so suppose the predictions that are coming out is around 80% correct. Okay, but it doesn't mean that we will leave our model as it is and we can continue with 80% accuracy. What we can do, we can continuously use this particular thing to train our model again. We will continuously use these things to train our model again. That means apart from predictions, these things are again feeded into the learnings, feeded into the model again. That means whatever model that is already created, okay, so that model will keep updated. Okay, this model needs to be keep updated, like M1, now it will be converted to M2 with more number of samples, then M3 with more number of samples. Okay, so that means what, we are transferring the learning to the new sets of data. Okay, but that data is having a different handwriting pattern, that data is not having a different language. Okay, that data is having a different handwriting pattern, that data is not having a different language, right? So that means the image that you are using almost related to it. Okay, so that means the image that you are using, the new image that you are using to transfer your previous learning, the new image that you are using to transfer your previous learning, it's somehow connected to connected to the image that is used to train your model. Okay, that means and if you want to combine more languages, that also you can do. Okay, you can combine more languages, but again, combining with more language will at the first stage it will just degrade your accuracy to a very low level, but slowly if you keep continuing transferring the learning from one stage to another to another, that means you are updating your model in one case. Okay, you can say that you are continuously updating your model. Okay, so you can impose with multiple languages as well. Okay, in simple thing, suppose you just make a model to identify animals. Okay, that doesn't mean that model can identify fruits as well. Okay, that model can only identify fruits if the sample is containing the fruits, otherwise that can only identify the animals. Okay, it may possible some new category of animal came into the things. Okay, but that animal will also have at least 4 legs. Okay, whatever the animal that is coming, that will also have 4 legs. Okay, that means those learnings can be transferred, that those learnings can be more updated with the new sets of images, but anyhow the new sets of images will be somehow connected to the previous sets of images. Okay, at some point the images are new, images are completely new, but at some point it must be connected. Okay, in that case only the learning will be transferred from one model to another model. Okay, that's how it works, right?
Okay, sir. Thank you.
Yeah.
One more question.
Yeah.
In papers, they used to say we use transfer learning and we did some kind of fine tuning.
Mhm.
What is that fine tuning actually?
Fine tuning is, the meaning of fine tuning is parameter tuning. Okay, parameter or hyper parameter tuning. Okay, parameter tuning or hyper parameter tuning. So what is parameter tuning and what is hyper parameter tuning? Let me tell you. Like if you are tuning the weights, okay, if you are tuning the weights, those are known as your parameter tunings. Okay, that means you are tuning the parameter to make your model more accurate. Okay, and what is hyperparameter tuning? Suppose we use the techniques like normalization. So in the normalization, the parameters that are required to tune normalization, the parameters that are required in regularizations. Okay, like we are using a lasso regularization, this regularization. In those regulation also there are alpha, beta, so many parameters are there. Okay, so we also have to tune these parameters. Okay, in the formula. So when we tune these parameter, that is known as your fine tuning or parameter tuning or hyperparameter tuning. So collectively the parameter tuning and hyperparameter tuning, that are known as your fine tuning. Like in our case, we are continuously doing the course of back propagation. What are we tuning? We are tuning the weights. Okay, we are tuning the weights, as well as we will also use something that is called dropout. Okay, we will also use something that is called dropout. Why we use dropout? Dropout is used to to avoid overfitting. Okay, dropout is used to avoid overfitting. Now how much dropout is required? Is it 20% dropout required? Is it 30% dropout required? Is it 50% dropout required? So tuning that particular value is also known as fine tuning. Okay.
Thank you, sir. Thank you
Yeah.
so much.
Yeah, right. So let's see. Okay, these things, the tuning things and these things we'll see now. Okay, like how we can tune and all during the course of coding. Okay, so let's see, whatever we discussed, how can we create a model using this particular thing. Okay, so for coding part I will use a platform called Colab. Okay, I will use a platform called Colab. Okay, with the Colab I am going to tune the things. Sorry, I am going to code. Okay, so what is Colab? Colab is your online tool developed by Google, okay, for coding. That means if you want to create a machine learning model, you are not required to install anything in your system. Okay, no software is required to be installed in the systems. So systems can be as it is. That means you are not going to use your own system. We are going to use the system of Google, okay, to process the things. Okay, that means we will only write the code using our system. We will only write the code using our system, but the processings will be done by whom? Processings will be done by the Google. Okay, Google system. Okay, so that is how Colab works, right? So let me give it a name. Neural network session 1. Okay, so how can we continue? Look here, whenever we are going to create a neural network model, there are certain frameworks or libraries that are used. Okay, one is known as your TensorFlow. TensorFlow is the most important framework, okay, given by Google, that completely creates a revolution in machine learning and deep learning. Okay, TensorFlow is a framework developed by Google, and that creates a kind of a revolution in case of machine learning and deep learning. Why? Because it deals with the tensors. Okay, then what is tensors? Okay, look here. If I will write something, just a minute. Just a minute. Just a minute. First of all, we should know what is tensor, then we can understand TensorFlow, right? If I will write something like this, a is equal to 7, what is it? This is a scalar. That is a simple mathematical value, right? If I write b is equal to 7, 5, 3, 2, 1, what is it? It is a vector, isn't it? It is a vector, correct? So in so many cases, we have to deal with the vectors, right? Then situations gets more intense, like you were talking about images, you were talking about some other things like a kind of a text. Okay, there can be a text, there can be images, there can be videos, audio, so many things can be there. So in those kind of things gets a little more complex, and the use of matrices came. 3, 2, 1, 7, 5, 6, 2, 3, 5. Okay, these are known as what? Matrices or matrix. Okay, these are called matrix. So when matrix came into the picture, okay, like when people thought, like in our data to train a model, when people thought that in our data to train a model, the data can be in the form of matrix. Okay, then NumPy was introduced to deal with this kind of data. Okay, NumPy was introduced to deal with this kind of data. Okay, but when situation gets more intense, okay, for example, you are using an image, okay, and that image is having a 3-layer, because image is a colored image. That image is represented by R, G, and B. That means suppose there is an image cross, the size of the image is 100 cross 100 pixel. Okay, that means it will be represented by a matrix with 100 values in columns and 100 values in rows. Okay, 100 values in column, 100 values in rows. Okay, so this is how image is represented, but it is not a single matrix. Image is not getting represented with the help of single matrix. Image will be represented by matrix over matrix. Okay, that is known as layered. Okay, so because the first layer is representing red color of that image, the second layer is representing the green color of that image, and the third layer is representing the blue color of that image. Correct? That means your image is represented now with the help of each particular pixel of your image is represented by 3 value. That means an image which is having a size of 100 cross 100 is actually giving you 100 cross 100 cross 3. That is equal to 30,000 features. A single image is giving you 30,000 features. It is not 10,000 features. Okay, so when this kind of situation arrives, okay, where you are having a layered matrix, that means a 3-dimensional matrix. Okay, a matrix over a matrix. Okay, this is known as what? Tensors. Okay, this is known as tensor. Okay, and when the tensor arrives into the picture, the processing requirements increases. Okay, that means the processing requirements means what? Now we can't go with simple vector kind of approach, we can't go with simple matrix kind of approach, because we have to, for each particular pixel, we have to process a lot. 3 values needs to be considered. Okay, 3 value needs to be considered at each layer, right? That means for a single, you can say for a single value or for a single neuron, this single neuron is affected by 3 different values. Okay, this single neuron is affected by 3 different features, R, G, and B. Correct? So that means processing of tensors becomes more intense and more complicated. That's why Google had introduced TensorFlow, okay, to deal with the tensors, to deal with the heavy sets of data, so that your processing can get much easier and you can write your code in a more proper or more kind of a you can say processing friendly way. Okay, that means now your code can be processed quite easily or more quite comfortably by your system, because TensorFlow on the back end will arrange and will do all the things, all the processing that are required. If TensorFlow is not there, then you have to write a very intense code, very complicated code to process each and every value, okay, to consider each and every value, that will be loop under the loop, loop under the loop. Okay, so many loops we have to create, and we have to create a very complicated code. Okay, so TensorFlow basically makes these things easier. With the TensorFlow framework, we can do a lot of things in a just single line of or 2 or 3 lines of code. Okay, that's why TensorFlow is used. Okay, first thing. Second, there are certain more libraries are introduced. Okay, like there is a library called Keras. Keras is there, Theano is there. Okay, certain more are there. Apart from TensorFlow, there are certain more frameworks are also there. Okay, so TensorFlow is a framework, like PyTorch is there. Okay, PyTorch is also a framework that is used, right? So these are the frameworks by different community to handle the heavy sets of data. Then it comes Keras, Theano. Okay, these kind of libraries are there. Okay, so those who helps us in creating the neural network, right? Neural network, like, okay, first we can assign, okay, for the first there will be hidden layer, sorry, input layer, then hidden layer, then output layer, right? So these are there, right? So these are basically done with the help of Keras. Okay, so nowadays the thing that is mostly used by the industry is based upon Keras and TensorFlow. Okay, Keras, before Keras, Theano was mostly used. Okay, but when Keras came, Theano was completely Theano goes at the second position. Okay, now Keras is mostly used by the industry to create your model, and because Keras is continuously updating itself. Okay, and it gives us the most prominent way to create a neural network. Right, now how can we create a neural network? To create a neural network, there is a 4 step. Okay, there is a 4 step workflow. Okay, there is just 4 step workflow that we need to understand. Once we understood this 4 step workflow, okay, then we can easily create any neural network. 4 step workflow, that is very important. So what is 4 step workflow? So we'll understand 4 step workflow over here. Okay, so one by one I will tell you the 4 step workflow over here. Okay, the first step, okay, let me tell you the first step. Okay, step 1 is known as define the define the training data. Okay, step 2 is known as define the neural network model. Okay, step 3 is what? Configure the learning process. That you just told me, the tuning process. Learning process means what? Tuning process. Okay, so configure the fine tuning process, configure the learning process. Okay, and step 4 is known as what? Train your model. Okay, so this is a 4 step process that we have to follow, just 4 step process, and only in this 4 step process things will keep changing, and ultimately we will get a complete model. So step 1, define a training model. So how can you define a training model? Let me define a training model. No, sorry, define the training data. It's a very simple. First of all, I will just use some dummy data with the help of NumPy. Okay, I will define X train and Y train. X train is what? X train is my feature, suppose, and Y train is I am considering as a label, right? So X train is having what? I will consider some random value, np dot random. I'm not considering any use case as of now. After this, after completing it, I will consider some use case. As of now, I just try to explain the process. Okay, 5,000 cross 32. Okay, that means what? There are 5,000 samples, and each sample is having how many features? 32 features. How many samples? 5,000 features, and each sample is having how many features? 32 features. Then y? np dot random dot random. Okay, there are 5,000 samples. Obviously, for 5,000 samples, if there are in features, then there will be 5,000 samples in labels also. And there are 5 possible output. Okay, that means 5 possible category. Okay, this is what we are getting. Okay, X and Y train. Thereafter, what we will do, we have to define the neural network model. Correct. So for defining the neural network model, what we will do, we will use Keras. Step 1 is done. X train, Y train is defined. If you want to see X train, this is your X train. Okay, there are, in a single line there are 32 features. Okay, and total 5,000 samples. Okay, in Y train, this is your Y train. That means for a single, there are 5 different categories. Okay, how many categories are there? 5 different categories. Okay, so the first sample is representing which category? This is having the highest value, so the category 3 is represented by the first sample. Okay, category 3 is represented by the first sample. Okay, for example, if you consider kind of what I should say, in case of text also, okay, like you are having 32 features, and those 32 features are representing the 5 letters. So suppose it is representing, just a minute, it is representing hello, how are you, question mark. Okay, so the first sample is representing, suppose R, because it is having highest value. Second sample is representing hello. Okay, third sample is representing what? Third sample is representing how. Okay, so this is how each sample, okay, each sample is representing certain value. Okay, each sample is representing what? Each sample is representing certain values. Okay, so it is what we are getting. Correct, it is what that we are getting, that is we have defined some random values over here. Next we have to define the neural network model. So how can we define neural network model? That is very important. For defining the neural network model, we will use something that is known as Keras. Okay, so how can we use Keras? You know, to use Keras, it's very easy. There is an official document of Keras where everything is written in a very clear and proper manner. Keras, just I will search for Keras, keras.io, deep learning API, get started. Okay, the Keras ecosystem, introduction, developer guides. You can just click on developer guide. The functional model, sequential model, I will explain. Okay, for example, I'm clicking sequential model. Okay, so it is written over here, everything. Okay, everything it is written how you can use it. Right. So what I will do, I'll just put it over here. Okay, you can put over here from Keras import models. Okay, that is used to define the models. Okay, that is, models means what? It is a sequential model or a functional model. I will explain the difference between the sequential model and functional model, don't worry. Okay, thereafter from Keras import layers. Okay, it will be used to define the layers. Layers means what? The input layer, hidden layers, output layers. Okay, these all things will be defined using this one. Okay, thereafter what we have to do, we have to define the model. Okay, how can we define? Just define like this: model is equal to, model is what? It is just a variable, is equal to models dot, if I am going to use sequential, I will use sequential over here, better. Correct, and then I can start adding the layers. Okay, thereafter I will start adding the layers. In neural network, at least one hidden layer is mandatory. If hidden layer is not there, it will be not considered as a neural network. Okay, at least one hidden layer, because without hidden layer it will be just a linear regression model. Without hidden layer it will be just a linear regression model, right? So model dot add. Okay, this is for hidden layer, model dot add. This is for output layer. Then where is input layer? Input layer will be added over here only. Let's see, layers dot dense. Dense is used for what? Dense is used to define the layers. Okay, dense is used to define what? Layers dot dense. You can see now, I'll show you over here. You can see, first of all, sequential is defined. Within the sequential, dense is used to define the layers. Okay, always dense are used to define the layers, right? So that's what we are using over here, dense. Okay, so in the dense, how many hidden neurons I want? Okay, how many hidden neurons I want? Okay, I'm having 32 input neurons. How many hidden neurons? Look here, there is no certain rule for that, how many hidden neurons you want, but generally people uses 16 in a multiple of 16. Okay, hidden layer you can use 15 also, you can use 10 also, no one will stop you. You can use 10, 20, 30, there is no calculation for that, but we use, in most of the cases you will see that people are using in a multiple of 16. The reason is simple. Since our neuron system is connected, like human neuron system is connected in a multiple of 16 neurons are connected. Okay, so it is just like copy that particular pattern, it is just a copy of that pattern. That's why people use it in a multiple of 16, like 16, 32, 64, okay, like that. So that's why we use 16, but it is not a rule that you can use anything over here. Okay, in many cases you'll see people using 100, maybe in many cases you'll see people using 50 also. Okay, it can consider everything, right? So 16 hidden neurons. Then we have to define the activation function. Okay, because activation function will do what? Activation function will break the linearity. Okay, so activation function I told you is ReLU. Okay, that we define at the hidden layer. Correct. Activation function is what? ReLU. Correct. So it is defined. So hidden layer is defined. Output layer. At the output, how many neurons we have to define? If there are 5 different possibilities, okay, over here how many possibilities? 5 possibilities. So as many possibilities are there, we will define that many neurons. So 5 neurons, just 5. We can't define 6 over here. If there are 5 possibilities, 5. Okay, and then activation is equal to what? We can use over here softmax. Correct. Now in sequential model, okay, when you define sequential model, then automatically sequential model connects the input layer with the hidden layer with the output layer. Then automatically this layer is connected to the output layer. But where is input layer? We have defined this thing, but we have not defined any input layer. Where is input layer? That is important. Okay, so look, input layer will be defined within this particular thing only, within this hidden layer only. That means we just define the properties of input layer within it. Okay, so what we will do, we will define it with the help of input underscore dimension. Okay, so what dimension that we are going to do, what dimension we are going to use? Input dimension is equal to, okay, what will be the dimension of input? That is very important, right? So let's check the dimension of input. We are having x underscore trained dot shape. This is the shape of your input data. So obviously input dimension, okay, the input neurons will be equal to 32 neurons because 5000 is the sample size. Each sample is having 32 features. Okay, each sample is having 32 features. So these 32 features will be considered as input neurons, isn't it? These features will be considered as input neurons. That means if I pass over here 1, okay, this is 0, index 0, this is having index 1, then I can get 32, isn't it? So what I will do, I will just use over here 1. I got what? 32. So this is going to be our input dimension, right? So what I can do, I can copy this part. So input dimension is equal to what? This thing. Okay, so it is simple model that we have defined over here. Okay, it is a very simple model that we have defined over here. Let's see, execute it. Okay, and just check the model summary. Okay, so it is our model summary. What the model summary is telling us? It is telling us there are total 613 learnable parameters or trainable parameters. Okay, that means there are 613 weights that this model will learn. How this 613 came over here? Just see. We are having 32 neurons at the input layer. Okay, this 32 will be multiplied with 16 hidden layers plus 16 bias. Okay, according to the equation, according to linear equation, you will get 528. You can just calculate, you will get 528. Correct. From the hidden layers, that is having 16 neurons, which is connected to 5 output neurons. 16 cross 5 plus 5 bias. Okay, 16 cross 5 plus 5 bias. You will get what? 85. 16 cross 5, 80, 80 plus 5, 85. Correct. So these are the trainable parameters or learnable parameters. And when you add these two things, what will you get? 613. Okay. So as of now, your model is having 613 trainable parameters that will be trained, okay, to give the predictions for the upcoming unknown value. These 613 parameters will get trained to give the prediction for upcoming unknown value. Correct. So I hope it is clear like how we can define a neural network model. Okay, it is how we define a neural network model. Okay, step third, configure the learning process. So what is configuring the learning process? Configure learning process means what? How my model will optimize, what will be the optimization technique, okay, and what will be the algorithms to optimize, what is the loss that it is going to consider. So for that we use what? From Keras input optimizers. So optimizers are what? Optimizers is a group of libraries that is having the the optimizing or error optimizing libraries like gradient descent. Gradient descent is what? It's a optimizing library, okay, that optimizes the error. Okay, so that optimizers is containing the library that can do the gradient descent, that can be used for gradient descent purpose. Okay, then from Keras input matrix. Okay, it will be used for what? For matrix. That means what? The accuracy and all those things we can see in the matrix. Okay, like what is the accuracy of, so matrix will return us the accuracy of my model, like how accurate my model is, how it is performing, just to validate the process and all, right? In that case matrices are used, isn't it? So how it can be used? It can be used with just one step. Model dot compile. Okay, we will call the compile library, compile function, and in the compile function there are certain parameters we have to pass. You can see the parameter that is showing over here. The first parameter is going to be your optimizer. Okay, so we have to call, you can see first parameter is what? Optimizer. So optimizer is equal to, you can pass the optimizer like SGD, stochastic gradient descent, right? And then we have to pass loss. Loss we have to pass, that is called loss, like how loss will be calculated. There are a lot many loss, like mean absolute error, mean squared error, okay, the difference from the actual value. The same way there is a loss called cross entropy. So you have to call it categorical cross entropy. Now what is categorical cross entropy? Let me tell you. If you are having output neuron, 5 output neurons, right? These 5 output neurons are having certain values like 0 0.7, 0 0.3, 0 0.5, 0 0.1, 0 0.6. Okay, actually I have written it in a wrong way. Let me correct it, because the summation will be 1, because we are using softmax. Softmax will calculate the probability, so it will be like 0 0.3, 0 0.1, 0 0.2, 0 0.25, 0 0.35. Is it 1? I guess it is 1, right? Just a minute, let me calculate. 3 to 5, 1, 6. No, sorry, it is not 1. Now it is 1. Okay. Now it is 1. No, still it is not 1, right? Now it is 1. The summation would be always 1, right? So it is what calculated. Now how error will be calculated? Now during the course of learning, it's a supervised learning. Okay, then that means sample is defined with one of the neuron. Okay, sample is representing, out of this neuron, one neuron is represented by the sample. Okay, suppose neuron 3 is represented. Okay, so if 3 is represented by the sample, that means 1 minus 0.2. This is equal to 0.8. It is known as cross entropy error. That means difference with 1. Difference with 1, whatever the difference that is present with respect to 1 is known as cross entropy, right? So we are calculating over a cross entropy error, right? That we want my model should consider cross entropy error, and thereafter I want the accuracy. So accuracy and all those things we can calculate with the help of matrix. Matrix is given over here, right? So it is optional, it is not required to give, it is not mandatory, but people used to give it just to, you know, just to monitor the accuracy. So matrices, well, not matrix, matrices is equal to accuracy. Okay, so it will help us in monitoring the accuracy. So our learning process is configured. Then at the last, train your model. So for training our model, we have to give three things over here: the features, labels, and number of epoch. Right? So model dot fit x train comma y train, okay, comma epoch. That means how many times I want to train a model? 10. Okay, so my model will get trained for 10 times. As well as we can also give batch size. Okay, so batch size can also be given, batch underscore size. What batch size do? Batch size basically it can be 128. It divides the data into kind of a, suppose you are having how many samples? You are having 5,000 samples. You are having how many samples? 5,000 samples. Okay, so that will be divided by 128. Okay, that means 128 sample will be considered in a single batch. That means in one instance model will consider 128 samples to optimize the error. Okay, 128 samples will be considered for optimizing the error, then again next 128 samples will be considered for optimizing the error. Okay, so that means now how many samples, you had given 5,000 samples, but your model will consider how many samples. If you divide 5,000 by 128, what will you get? What value will you get? Let me divide and tell you. This calculator. 5,000 divided by 128. This will be 39. Okay, it is 39.06. So it will be around 39, right? So let's see. Sorry, it's epoch, spelling is wrong over here. I guess EPOCHS. Yeah. So you can see 39 I said, that's why it is saying what 40. Okay, that means total 40 things it is considering, because a batch of 128 used over here. Okay, total how many epochs went on? 10 epochs. Okay, and accuracy is what you can see over here: 20%, 19%, 19%, some accuracy that you can see. Obviously the accuracy is not good because it is just a kind of a, the thing that is just a random value I use. So it is not about the accuracy, it is about the process. Okay, like how the process is going on. So you can see the process is going on, and at the end we are getting the accuracy. Okay, if I don't use batch size, then what will happen? It is automatically considering some batch size and giving you 157. So if you divide 5,000 by 157, so by default what batch it is considering we can get. Okay, by default it considers some amount of batch or some amount of values in one batch. So 157, 31. Okay, by default it is considering a batch of 32. Okay, by default it is considering a batch of what? 32. Okay, but if I give 128, it will consider a batch of 128. Right? So you can see this is how training is basically done. So making a neural network is a very easy process. Okay, once you are having a data, with the help of Keras, in just 4-step flow, 4-step workflow, you can create a neural network. Okay, let me give a name to it: 4-step workflow Keras. Okay, so it is how to work. So let me share this code also with you. You can see this is your accuracy. Everything is working good, right? So if I will share this code with you, I'll click over it. Copy the link. I'm sharing it in chat box. You can access it and can use it. You can go through it, and if you're having any doubt, please do ask. There are certain more things that are going to be added within it. Okay, we are going to discuss certain more things around it very soon. Just go through it. Thereafter, we'll go for the next part. Okay, so it is done now. Let's go for the next thing. I'll create a new program. Okay, now let's create some actual program. Okay, some things like some actual use case. Okay, so for this actual use case, I am again going to create sequential. I will create functional after the break. So first of all, I will again, because sequential I explained first, I will explain the functional, then I will create it. So sequential model Keras. Okay, so what is sequential model? I already explained, like the first layer will be connected to the next layer, the next layer will be connected to the upcoming layers. Okay, and that's how sequential model proceeds, right? So we have to create a sequential model in Keras, right? So for creating a sequential model, all of the things that we had seen, okay, this time we will consider a use case. Okay, use case of what? MNIST handwritten data. Okay, handwritten numerical data, better I should say, numerical data. So MNIST is what? MNIST is a data set that is containing handwritten digits. Okay, handwritten numerical digit data. Okay, that means we can create a model to identify the handwritten digits. Okay, so how can we proceed? We can proceed like this from Keras. First of all, we have to import all the libraries. So from Keras, import models. Okay, then from Keras, import layers like we did. Okay, from Keras import layers we can do, or you can directly write over here from Keras dot layers. This is also you can write import the type of layers. So what are the type of layers that we are using? You can see the type of layers that we used earlier was only one type of layer that we used earlier, that is dense. Okay, this is the only one type we used, right? So model. Okay, so import dense. Okay, this time we are going to use one more layer that is known as dropout. Okay, dropout I will explain now. Okay, dropout. So what is dropout? I'll explain. Okay, next we need data set. So from Keras dot data sets, it is inbuilt within the Keras. I am using a data set from the Keras only. I am not using some outside data. Okay, later on I will use some data from outside. Okay, MNIST. Okay, so MNIST will be imported. Okay, what is MNIST? Just hold on, we'll get into it, right? Don't worry about it, right? As well as one very important library we are going to use over here from Keras dot utils import to categorical. What is this? This is a library that is used for one hot encoding. What? This is a library that will be used for one hot encoding. What is one hot encoding basically? One hot encoding means kind of, if you know, if you're having a category like this, just a minute. Excuse me. If you're having a category like this, A, B, C. Okay, so A can be represented by 1 0 0 because machine needs a numerical value. It can't go with a the string value or the character value. So B can be represented by what? 0 1 0. Okay, and C can be represented by what? 0 0 1. Okay, so it is known as your one hot encoding. Okay, it is known as what? It is known as your one hot encoding. Correct. So for doing one hot encoding, we are using a library. Okay, and the library name is what? To categorical. Okay, it is what it will do, categorical. Okay, and what is this MNIST? MNIST is nothing, it is just a data set and written digit data. Okay, done. Correct. So this is what MNIST, right? So our libraries are important now. Next, what we can do, we can create your model and all, right? As well as we will use one more thing. Okay, let it be done. Import live loss plot. Now, what is live loss plot? Live loss plot is basically a library that gives us the live feed. Live feed means what? The live learning feed. That means how the loss is increasing or decreasing, how the accuracy is increasing or decreasing. Okay, that is what it do. It gives you the plot. Plot of what? Plot of accuracy. Okay, like after each epoch, the plot will update, right? So plot losses is equal to live loss plot dot plot losses keras. Okay. So it is what that you can note down somewhere, because obviously we can't either you can remember this because these are the inbuilt libraries, so we have to use it. So no module name live loss plot, that means it is not there. So how can we install it? We can install it like this: pip install live loss plot. So it will take a little time to get installed, not just 1 minute of time. Okay, and it will get installed. So it installed, pip install live loss plot, and then after you can see it is installed. It is for the plotting of what? Accuracy. Okay, accuracy curve, that's it. Okay, next what we can do. Next we can define our training and testing set. Correct, we can define our training and testing set for the model and all. So let's see. X train comma Y train. Okay, X train and Y train I am using as a training set. Okay, and then X test and Y test I am using as a testing set. Okay, testing set, right? And then I can call MNIST dot load. I will tell you how to use your own dataset also, don't worry. First of all, we will understand certain point from here, and then only thing is will remain that how can we use our own data. So that also I'll tell you. Okay, by the end of the day we'll also get that thing, don't worry about it. So it is a inbuilt data, so it is having certain process. So you can see automatically data will be divided in two part, the training and testing part. You want to check the shape of it, so what we can do, we can just check the shape of it, each of them. Print xtrain dot shape. Okay, this is a training set, that means how many sample are there in training set, and then after how many samples are there in testing set. Okay, x test, y train, y test. Or I should write this thing before this particular. So X train corresponding output Y train, X test corresponding output Y test. Okay, so there are 60,000 samples. There are how many samples? There are 60,000 samples in training and there are 10,000 samples in testing. Okay, 28 cross 28 because over here the image size that is used is of 28 cross 28. That means what? If I will plot it, suppose I have written over here 5. So this particular figure is divided into 28 cross 28. Okay, 28 cross 28. Okay, so each pixel is one feature. So that's why 60,000 samples cross 28 cross 28. That means it is 60,000 features cross 784. Okay, 784. Okay, total 784 features are there in each sample. Right. So it is what we are getting. Okay, so now what we have to do? We have to do a little bit more thing over here. We have to convert the Y train into a categorical value. Okay, and we have to change the shape of X train. Okay, we have to change the shape of X train. That means what? X train is equal to X train dot reshape. It will be reshaped into what? It will be reshaped into 60,000. Okay, samples will remain as it is, but the second thing, okay, because you know this is 28 cross 28, right? So what I mean, just a minute, you know, it is going to be your input neuron. So input neuron is basically arranged like this in a single dimension. Okay, so that means this 28 cross 28 will feed over here. That means this 28 cross 28 first needs to be converted into 784. Okay, and then this 784 will be arranged over here. Okay, this 784 will be arranged over here, isn't it? So it is what we have to do, right? So for doing it, what we will do, we will just convert this thing into 60,000 cross 784. Okay, so it will be reshaped 60,000 into 784. It is reshaped, right? Same way X test will be reshaped. X test will be reshaped into 10,000 into 784. Correct. So X test is reshaped. Then after Y test, Y train and Y test, we have to deal with Y train and Y test. Okay. What happened? Oh, sorry. Here X test needs to be passed. I'm sorry. Okay, and then Y train and Y test. Why? So it is what? Reshaping your input values, reshaping input data. Okay, and then generate categorical values of labels. Okay, generate categorical values of labels. So labels are what? Y train. So Y train and Y test. Y train is corresponding output of X train and Y test. So it is what? It will be two categorical that we had already imported over here. You can see. Okay, from keras.utils two categorical. Why imported? For one hot encoding. So I will just use it. Because you can see what Y train is representing by default. Y train is representing the labels, like the first sample is representing 5, second sample is representing 0, second sample, third sample is representing 4. Okay, in this way each sample is representing some of the handwritten digit. Okay, it will be between 0 to 9. Okay, each sample is representing what? Some of the handwritten digit, and that will be between what? 0 to 9, right? So Y train is equal to 2 categorical. Okay, and what we can pass over here? Y train. Okay, and how many classes? There are 10 classes, 0 to 9. Okay, and then you call, okay, Y, the same thing we can do for Y test. Y test is equal to categorical Y test. Okay, fine. So if you call Y train over here, what are you getting? You are getting this thing. first sample was representing 5. So if you call the first sample, okay, it is getting what? You can see over here, the fifth position is having a higher bit, 0, 1, 2, 3, 4, 5. Okay, the second sample was representing 0, so it must be the 0th location will have the higher bit. That said, the third sample represents 4. So, okay. So I hope you understood what is categorical value and why categorical value is required, why one hot encoding is required to calculate the error with respect to cross entropy. Okay, because cross entropy error can be easily calculated. First of all, there will be 10 neurons at the output layer. Okay, so 10 neurons can be defined. Okay, as well as the categorical, or you can say the cross entropy error can be easily calculated. Right, so it is done now. Okay, okay, and then what we can do, data summary. This is just for checking. Okay, X train. Let's see if it is working or not. X train, Y train, X test, Y train, Y test. Okay, data summary is not working over here. I guess this library has changed, or anyway, just leave it. We will create your model. Okay, so what you will do, we have to create a build neural network model. Build neural network model. So we have to build our neural network model. How can we build our neural network model? We can build easily. First of all, you have to define the type of model as we defined earlier. So model is equal to models that we imported the library dot sequential. Okay, then we have to add model dot add the hidden layer. Then again we have to add model dot add again one more hidden layer. Then we have to add again model dot add. So this is your output layer. So hidden layer over here will be defined with dense layer. Okay, so dense, how many neurons we can define? We can define a neuron of our choice. Okay, here I will define 512 neurons. Okay, activation is equal to ReLU. Okay, and then input dimension or input shape what I had defined earlier, input dimension, right? So I'll just copy this thing as it is and we'll paste over here. Okay, X train, here it is just X train. Okay, it is just X train dot shape, right? Right, and thereafter over here one more dense layer, that is one more hidden layer. It can be 256, a little less, comma activation is equal to ReLU. At the output it will be 10 because there are 10 categories only. 10. Activation will be what? Softmax. Okay, now this is the simple thing. Okay, but here we will also use dropout. But before using dropout, we should know what a dropout is, isn't it? So let me tell you about dropout. When we create a model, okay, what happened? These neurons are connected with the hidden layer and then the output layer. So over here 512, okay, 512 values are there, and over here you are having how many? 784. Okay, so 512 plus 784 plus 512, there are huge number of, there are huge number of weights. Okay, so when you are having huge number of weights, what happens in some cases, suppose you are having a very huge number of weights, that means you are going to create a very huge model. Okay, in that case there is a chance of model getting overfitted. Overfitted means what? It generates a weight for each particular situation. For every situation, like we're having a 9 situations, right, or 10 situations, for all those 10 situations it configured some weight. Okay, but those weights are highly dependent upon the training data. That means those weights have been configured in such a way to get a maximum accuracy over training there, because these weights are getting configured in such a way to give you maximum accuracy over training data. But when a known value came, these weights are not welcoming them as it is welcoming the training data. Okay, so what we do, we use dropout. Okay, with the help of dropout, what we do, we just limit the number of weights over here that is functioning. Actually, we can use 30% dropout. Okay, in that case only 30% of the weight will be activated. Okay, sorry, dropout means only 70% of the weight will be activated. Rest 30% will not be considered by the model. Okay, that will be just random choice. Okay, model will choose any random 70% weight for the purpose of making the model prediction. Okay, so that number of weights can be regulated. Okay, so that's why the dropout is used. Okay, so you can use a dropout after each layer. Okay, you can use a dropout over here, and after each layer you can use a different size of dropout. Okay, just to avoid overfitting, like model dot add. Just like dense layer, we had also imported a dropout layer. If you see, dropout is also imported, right? So model dot add dropout. Okay, how much dropout? Suppose I want a 50% dropout over here. So 50% weights will be dropped out, will not be considered. Okay, only 50% random weights. After this, I can also use dropout over here. Over here, I'm using 30%. That's it, right? So this is how my initial model is created, and thereafter I can check model summary. You can check it. Okay, this is our model summary. Total 5,35,818 training parameters. Then you have to compile your model. Okay, how can we compile? We can combine model dot compile. Okay, first of all you have to give optimizer. So optimizer is equal to SGD. Okay, then the loss equal to categorical cross entropy that we used earlier. Okay, and at the end we are going to use matrix accuracy. Okay, and then we can fit it model dot fit. Okay, for fitting what are required? It is required X train and Y train. Okay, it required batch size, that is optional, batch underscore size, that will be equal to, suppose I am giving 128. Okay, then epochs is equal to, suppose I am giving an epoch of 20 epochs, that 20 times the training will run. Okay, then for the plotting I can use callbacks, that is for the live loss plot is equal to plot losses that I had given earlier. This will be handled by library. We are not going to do anything with it. Okay, and then we can use what? Validation. Okay, so validation is equal to what? That means the testing accuracy over the testing data. Okay, this is very important, right? X test comma Y test. That's it. Enough. Okay, we will execute it. Okay, validation data, I guess it's missing over here. Validation underscore data. Okay, so training is started. You can see the first epoch, the accuracy is what happened? what is losing over here? Just a minute, let me check the shape of ytest dot shape. That's fine. Xtest. Oh, cross 10 out. That's fine. It's fine. We can use xtest dot shape. That is also fine. Then why it is creating a issue? Okay, let me remove this part. I guess something is there with the. I will only use this thing. I will check it out. First of all, let it be done. So training is going on. Okay, this is the training. So it is accuracy plot. Okay. The validation data is not used. That's why it is showing a problem. Anyway. So it is your accuracy and all those things are going on. All right. So we will see why your validation data, because why I use plot over here, because so that I can check the accuracy plot between training and testing, right? But validation data, it is not picking up. Why it is not picking up, I have to check. So let it be completed, thereafter I will check. Done. So it is showing an accuracy of around 9%. That is a very low accuracy. Anyway, we will improve it. First of all, let me evaluate model dot evaluate on the ground of testing data, right? So x test comma y test. Okay. So it is also showing accuracy of almost same. Okay, it is also around 9% accuracy, right? So why it is having a very low accuracy? Okay, why it is having a very low accuracy? The reason is we are using a data value like this. If you consider any data value x train, this is your data value, right? And it is what, suppose I consider any single sample, like sample 5. Okay, so it is our data value, right? So the figures over here is very big. Okay, it is in the range of 0 to 255. Okay, that's why the optimizer was unable to, in the kind of whatever the things that has been given, it is unable to optimize it properly. So this needs to be normalized. Normalized means what? This needs to be in the range of 0 to 1. Okay, so how it can be done? If we want to keep the ratio same and we want to normalize, what we can do, we can divide each value by the maximum value, isn't it? That means if it is a x train over here, what we can do, x train underscore n, that is a normalized value, is equal to x train divided by x train dot max. Okay, it will be divided by maximum value, like it can be whatever, like 255 or whatever, and x test n divided by x test X test, right? So we are just dividing and normalizing it. That is very important, right? So once we normalized it, right? Okay, and thereafter we train, you can see the change. Again, I will define the model. Compilation is done, and over here I will call xtrain n underscore n and ytrain n underscore n. For some time, let me remove this plot part, because plot part will be helpful once validation data can be called. Validation data is not getting called over here. We'll see this thing next, but first of all, let me train it. Oh, it should not be ytrain n. Ytrain will remain same. It is just xtrain n. Okay, it is a normalized value. So you can see the last time our accuracy was strict to up to 9%. Okay, now it is started in the first epoch, it touches around 50%, 56%. Okay, and the second epoch 79, then 83, then 85. That means my accuracy just enhanced by just normalizing the data. Okay, what is normalization? It is simple. If you are considering this thing, suppose you are having a value like 5, 7, 3, 2, 9, and we have to normalize it. So, and we want to make the difference or the ratio of differences same. So what we can do? 5 by 9, 7 by 9, 3 by 9, 2 by 9, 9 by 9. So the meaning of data will remain same. Okay, and it will be a scale down between 0 to 1. Okay, it is like a scaling down the value. Okay, so that your processing, your optimizer can optimize, can work good on the mathematical value, okay, and can give you the better accuracy. So it touches more than 90% of the accuracy. So we'll see so many things after the break, right? We'll see, like, apart from normalization, what else we can do. What are functional model? How can we use functional model? If I'm having my own data, how can we use my own data? If I'm having my own image set of data, how can we use the own image set of data? And how can we make the predictions as well? As of now, I'm not telling you the predictions part. So after the break, we'll see the predictions. As of now, we are winding up only up to the training part, and this training is telling us the value, the final accuracy is around 95 to 93%. That is very good. And this is your normalized value, if you can see. Okay, you can see these values are your normalized values. Better? Okay, so after the break, we'll see the predictions. How can we make the predictions? How can we use our own data set? And how can we optimize it more for much better accuracy? Right? So let me share the code with you. Okay, that's it from my side for this session. So we can resume back by one, right?
Yes.
Okay, so today we are resuming back a little earlier. I'm really sorry for that, because we will wind up by 3. Okay, after 3 we'll be free, right? So we can wind up by 3. Just resume back a little earlier, because after 3 I'm having certain kind of schedulings, and also we'll within after half an hour we'll resume back and we'll complete this particular topic. Okay, ma'am?
Okay, thank you, people.
Okay, thank you everyone. You can just note down your queries, and I will take your queries in the second half. Thank you everyone.
Thank you. The feedback link is posted in the chat window. So you kindly fill that feedback form. Today afternoon session is as told by Pipil Kumar, starts by 2 p.m. Sorry, not 2 p.m. It is 1 to 3. Sorry. And